Hi, recording is rolling. Today is Tuesday, October 11th. We're coming back from a 3-day weekend. So we just finished the first quarter. Here's top scientists for forces. So if your name's on there, then good job. You guys did a really good job on forces. Okay, so first we're kind of in the middle of this next unit, which is let's see, centripetal force, like circular type motion. I need to teach you guys about universal gravitation. I'm trying to get there one day at a time. And then we're going to put those ideas together and make orbits out of all that. Right. So that's where we're going with this. Okay. All right, before I get rolling on too much class stuff, tomorrow, you guys are not going to be in this classroom. You guys are going to be where tomorrow? Yeah, cafeteria. Right. And I have something set up for you guys there, but we'll get to that. Okay. So you guys, tomorrow is the PSAT, proctor on that tomorrow. All right, so I gave you guys a few pages, so let's just check these off. So I gave you guys the right before I started the recording. And so one page looks like this. It's 20 conceptual questions on gravitation, and on the other side are some gravitation and orbits, algebra-based questions. We're going to solve some equations. Just like we normally do, we're going to solve all these in class together. Right? Probably do a Kahoot with these 20 conceptual questions, right? All the answers are going to be there. Okay? And then eventually, you guys know the pattern of those classes. Eventually, I'll get you guys a quiz, and the quiz questions are mostly for those questions. They're just ways of doing things. Okay? So you guys can have all the answers. Another page I gave you guys looks like this. It says rotational kinematic. Okay? Now, this is going to be just today's in-class activities. This is just going to be extra notes for you guys. Right? So we're going to spend a good time in class later today working on this. Okay? But before we do all that stuff, the other page I gave you guys is like this heavy cardstock type. Okay? You guys got this like heavy cardstock paper page, right? And so this is gonna relate to what you guys are gonna do tomorrow. So when you guys are in the cafeteria tomorrow, have this page out, cardstock page. And I'm gonna do this right now. Before we get started on this, take your ruler and mark off about 2 or 3 centimeters, about 1 inch on the right side. Mark off a margin. It's that margin right there. I just went zip and put a margin right there. Okay, you guys see that on this heavy cardstock page? About a 1 inch, about 2 to 3 centimeters margin right there. All right, get that. All right, now what this is going to be is a panel of an O'Neill cylinder. So I introduced this idea to you guys back on Friday. It was a few days ago. Let me talk a little bit more about that. We're gonna here. I've got a picture right here. Show you some more examples, and we're eventually going to solve this problem too. Okay. So O'Neill cylinder, suppose you're out in deep space. There's no like real gravity around, or maybe extremely weak, right? But no like big planet, right? So you're just like, everybody's just kind of floating around. Right. Now, if everybody, here, suppose there's this giant cylinder, right? And if that's just floating around too, everybody could just be floating around. There's nothing special going on. But if there's some friction going on and it gives things a spin, right? And they go along for the ride, then, well, now they're in motion with this thing. Now, you guys know from Newton's first law of motion, what would happen if you suddenly remove the walls? So you just like drop the walls away. Right? Would this guy see this thing rotating this way, right? Omega. Right? Would this guy make a 90-degree turn and fly straight away from the center? Or is he going to fly off tangent to his motion? Yeah, it's going to fly off tangent to his motion, right? That's what Newton's first law of motion says. Okay. Now let's put the walls back in place. Okay, so now the cylinder is back there. Okay. Well, now he's being blocked from that motion, right? You can't fly off tangent to the motion because the wall's in the way. It's like pushing it back towards the center. And what's that force called that's pushing it back towards the center? Because centripetal force, right? Right. In this case, it's provided by the normal force from the walls. You could have said normal force, that would also be true. But I'm looking for like a centripetal force to keep him in. And it's like this curved type motion, right? Okay. So that brings us back to this panel. What I'm going to have you guys do is to draw a piece of an O'Neill cylinder here. Think about, suppose so tomorrow you guys are going to be engineers. You guys are going to engineer one of these things. Think, well, what would I want to have on board this the space habitat of an old space? Hey, maybe you want all the things that you could have down here on Earth. Right, so some kind of energy source, some way of like drinking water, some way of like eating food, maybe marketplaces, maybe like transportation hub, right? So you have one panel of a larger project. So here's like your panel with a margin on the right side, right? You can draw whatever you want here. But so use your imagination, think what what do you want on board this O'Neill cylinder? Okay. And then here's all your classmates. Right? Panel, panel. Right? You just a bunch of panels. Then can I glue the back of this to the front of this? And glue, glue. See how that can just like glue together like that? Okay. They can glue together into one giant strip. Right. Panel, 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 panel. Right. They can take those panels and put them all into a giant cylinder, like a giant ring. Give this thing a spin. Okay. So I will hang that from my ceiling, and that will be your class O'Neill cylinder. Okay. Let me flip my screen to show you guys some examples of these. Examples. All right. All right, so yeah, here's an example panel. Notice it's like an aerial view, like you're looking down on something. I mean, that would make the most sense, right? Okay. Ooh, I see some buildings. I see some roads. Okay. Here's another like aerial view type panel. Okay. Got enough space, please. Yeah, so if it's not strictly aerial view, that's all right. Yeah, it's really just a use your imagination type day. Okay, so that'll be tomorrow. I've also got a video of this, right? So what I'm about to show you guys, this is not the best example, but it's it works, right? Right. Like, so we glue it all together, and there you go. All comes together. All right, so when you guys are in the cafeteria tomorrow, you guys got that cardstock paper, you can design your own panel, and then in time, I will glue these all together and hang it from a ceiling, and it's gonna look awesome. All right, any questions about that, about tomorrow? All right, put this back to straight for next class. All right, see, stop share, flip the screen back over. All right, so that is that right there, right there. All that ready to go. Whew. All right, you guys good? Who's got any questions so far? Any questions about anything? All right, so we're eventually headed with this class. This is gonna take some time. I'm not gonna see you guys tomorrow. I'll see you guys Thursday, and Friday's a half day. At some point, I need to get you guys notes on universal gravitation. We need to talk about that. Haven't quite got there yet. We're gonna put all of that together with this rotational stuff and make orbits, right? But today, rest of the day, let's do some review for stuff you guys saw on Friday, because I know it's end of the week, you guys saw it once. So have a big old review session here, right? How rotational stuff works. Okay. Suppose let's go back to this O'Neill cylinder. Now we're going to finally answer this question. Okay. And let's say you know how big this thing is. I gave you guys a 500-meter radius. I could have said a 1 kilometer diameter. Wouldn't that be the same thing? 1 kilometer diameter, that's 1,000 meters diameter, 500 meters radius. Oh, look at that, 500 meters radius. Okay. And if it's not spinning at all, everyone's just floating around. If it's spinning too fast, like a centrifuge, and everyone's going to feel flattened out. But there's probably some spin rate where you can target this artificial gravity, 9.8 meters per second squared. Right. Now, this is a centripetal acceleration caused by the normal force, centripetal force. Okay. It's not real gravity, but if this thing is big enough, it might be kind of hard to distinguish the difference, right? If you're blindfolded. Okay. So I really got two questions. One question is, well, how fast does this thing have to rotate to achieve that artificial gravity? And then the second question is right here. How much time would it actually take to rotate once? Okay. We did a very similar thing back on Friday, but let's do another one. Right. So in that review, you guys saw those new posters hanging up on the wall over there. Let's take a look at those. Okay. So we're showing my breakout this turntable too. Right. So you guys remember these 3 Roosevelts? We're saying like, well, how far have the Roosevelts moved and how fast are they moving? Okay. But now how far and how fast? Well, there's 2 contexts to look at. I could point a radar gun at each one of these to get how fast. And this guy reads 0 meters per second. And then the further out, the faster it's going to go. But notice that they're also all on the same rotating disk. So they all make the same number of turns at the same time. So they all have the same angular velocity, even though they have different linear velocities. The same is true for like distance, right? They've gone different distances. this guy's not going anywhere. This guy's going a long way. Even though they've made the same number of degrees, they turned the same number of degrees, right? Or they made one revolution. They could all make one revolution. They can have the same angular displacement, even though they have different linear displacement. Okay. Now the connection from angular motion to linear motion, all you have to do very simply is multiply by r. Right. So if you know how far you've turned, right? And remember, there are different ways to quantify how far you've turned. You could quantify degrees, sure. You could also quantify revolutions, but the best way is radians. And the reason that the best way is radians is because that's what naturally feeds into equations. It naturally falls out of the equations when you just run the equation numbers. Okay. So we're gonna usually use radians for the next couple of weeks here. Okay. By the way, what you're looking at is actually pretty close to 1 radian, which is about 57 degrees. 57 degrees is about 1 radian. Okay, you're looking at it. Okay. Do you guys remember what is the circumference of a circle? Circumference equals what? Yeah, so 360 degrees, right? And then so that's like an angular displacement. It could be like 360 degrees, but 360 degrees, that's equivalent to 1 revolution, right? Which is equal to how many radians? 2 pi. 2 pi. 2 pi. Now take a look at this connection here. X could be some general distance you've walked around the circle. What if you walk exactly 1 trip all the way around? That's called 1 circumference, isn't it? Circumference equals 2 pi radians times r. Hey, circumference equals 2 pi r, right? You guys have known that since elementary school, right? So you guys have actually known a specific version of this more general equation. Now you can get any x for any theta and any r, right? It doesn't have to necessarily be 1 full circumference, although that is an example of this. Okay? You can also say how fast you're going. So break out the radar gun pointed at each of those Roosevelts. Well, how fast they were going on the radar gun is how fast this whole thing is rotating in radians per second, has to be radians per second, multiplied by your location from the center. Okay. And then there's also an acceleration analog. So linear acceleration is angular acceleration times radius. Okay. I should point out this. Okay. Neither of these accelerations refer to centripetal acceleration. That's a different idea. Centripetal acceleration is caused by the centripetal force, maybe like frictional force, that's holding those Roosevelts on the turntable. Okay? What this angular acceleration refers to is if this turntable is speeding up or slowing down, the rate that it's doing that. And the linear acceleration is if you multiply that by the radial distance, it'll tell you, like in a linear sense, if you're like in a car, like tapping the brakes or hitting the gas pedal. Okay? But that's a different idea from centripetal acceleration. You guys remember if you take those 3 kinematic formulas from back in the day? Here, watch this up here. And pop in the rotational equivalents, you get 3 completely valid equations. Okay. We're about to sort of play around with these here in a few minutes. Right. We're going to do a whole demo full of these. Okay. And then finally, some of the new stuff. What force would allow something to move on a curved path? Because remember, Newton's first law of motion says nothing ever wants to move on a curved path. So if something is moving on a curved path, there's some kind of center-seeking force that's pushing or pulling it into a circle. Your guys' lab, there was a tension in a string that was pulling it. That? Right. And you guys derived this top equation in your lab last week. You said that centripetal force is equal to, well, the mass of what's on the curved path times how fast it's going squared divided by the radius of curvature. That's what you guys figured out in your lab. You guys remember to do that? Okay. Now, what I can do is I can combine a couple of ideas here. Pause real fast. Remember, centripetal force is never a force unto itself. It's always provided by one of your classic forces. It might be a tension, it might be a friction force, it might be a normal force, it might be gravity force. Okay. Okay. But take a look at that V. You guys see that V? Well, didn't I just a minute ago say V is also equal to omega times R? Can we take that omega R and substitute it right there? Okay. This is all in your notes from Friday, by the way. This is all just review. Okay. And if you do that, you can come up with a new expression also that's also perfectly valid, but it's in terms of the angular velocity, not the linear velocity, right? Okay. And this one is particularly useful for turntables and O'Neill cylinders. And that brings us back to this guy. Okay, is that all right? All right, so let's finally start to tackle this problem. Which, again, if you look at your notes from Friday, you might be able to figure this out even before I get to the answer, guys. So, I see a radial size of this thing, so I know how big it is. That could feed in very nicely right here. Okay. one of the questions floating around is, what is the angular velocity? Like how fast is it spinning? So kind of solve for this. So we don't have a number for this yet. Okay. And ooh, mass. Hey, do you guys think that all these individual people have different masses? They probably do, right? Maybe this guy's 50 kilograms, this guy's 60 kilograms, right? They're all different masses. But do you think that they might all feel the same artificial gravity, same acceleration, centripetal acceleration? And if that's true, then look at those four saying, well, maybe I don't care about their artificial weight so much as artificial acceleration going on here, centripetal acceleration. Guys, how do you go from force to acceleration? According to Newton's second law of motion. Divide by mass. Is that true? Acceleration is force divided by mass. Can I do that with this whole expression right here? If the centripetal force is mass times angular velocity squared times radius, okay, say centripetal acceleration is just drop this mass. It'd just be omega squared times r, right? Probably say that in your notes from Friday too, right? Take a step. Okay, so that's where we can plug in these values now. What number feeds in right there? Is that 9.8 meters per second squared? Right? 9.8 meters per second squared, right? Because our target value is Earth gravity. What we want to trick all these people and make them think that they're on Earth, right? Even though they're not. Right. We're solving for how fast is this thing rotating. That value is being squared, so we're gonna have to do some algebra later. And what number feeds in right here? 500 meters. Okay, 500 meters, right? 500 meters. Just like that. Okay, so there's the setup. All right, you guys see this all coming together? Okay. All right, so can you guys do a couple of algebra steps and solve for this omega? Okay. I know omega squared is 9.8 meters per second squared divided by 500 meters. Okay. And then what's the last algebra step? Do what to both sides? Square root. So omega, that's angular velocity. We spell that out. Angular velocity is equal to the square root of all this fun stuff. Meters per second squared, meters. All right. So if you guys are beating each of the answers, that is a real good sign. So the number on my calculator screen is showing this right here. Okay. But you guys know in physics, these numbers have units attached to them. So what unit's attached to this number? If you want to say how fast is something turning. Ooh, close. It's like radians per second. Radians per second, right? Now, usually if you just follow the math, the units also follow along the math. Like for example, the meters cancel out, meters cancels out. Then 1 over second squared, that's a square root. So we're definitely gonna get per seconds. It might be kind of tricky to figure out is like, where's radians come from? So radians is one of those weird units that maybe there's like a justification, but it can either appear or disappear from the math. We're just naturally going through the math, right? But notice that it's not degrees and it's not revolutions, right? So what naturally falls out of the math is some kind of radian value. In this case, radians per second. Remember, I keep telling you guys, radians is the best way to measure angles, right? And here's why, because it naturally falls out of the math. Okay, so that's how fast this whole thing is rotating. 0.14 radians per second. Now, I don't know, maybe that's a little bit abstract. So let's see what that actually looks like. You guys know 2 pi radians and 360 degrees. That's the same thing, right? So if I take this and multiply in the 360 degrees and divide by open parenthesis 2 pi radians, that, by the way, isn't maybe super relevant, but that's about 8 degrees per second, right? Just as you guys are probably more familiar with degrees than radians, right? Maybe it's a little easier to visualize because I know what degrees are. That's like 8 tick marks, right? This little tiny, little skinny angle right there, right? 8 degrees, right? What does 8 degrees per second look like? I don't know exactly, but I bet that right there, you're probably looking at it, right? That's probably pretty close to 8 degrees per second. Do you guys think? Right. So if this thing had a radius of 500 meters, right? That's about how fast proportionally, you'd want to see it be rotating in space, so that all the people on the circumference felt like they were on Earth. Okay, you guys get that? Okay, 0.14 radians per second. Okay, but there's still one question to go, which is how much time does it take, therefore, to go around once? You guys ready to tackle that? Okay, now, if you look at your notes on Friday, I solved that with dimensional analysis, but today, let me try something a little different. You guys remember distance equals speed times time? Right? I bet you guys knew that before you ever stepped foot in this class. Right? Do you know how fast you're driving your car? How much time you drive for? You can figure out how far you went. Okay. Let's pop in the rotational analogous variables. How far have you turned is equal to how fast you're turning times the amount of time. Right? Is that true? Okay. Now, how much time to rotate once? Well, how much time? I guess we're solving for that t, right? How much time t? Okay. Now, to rotate once, is that called one revolution? Right? So what number goes in for the angular displacement? Because you don't want to do revolutions. You want to do what unit? Radians, right? So, guys, rotate once, make one complete turnaround. How many radians is that?
One.
Circumference equals
2 pi.
Yeah, 2 pi r. 2 pi radians. Okay. Yeah, it's also 360 degrees, 1 revolution, 2 pi radians. Those are all equivalent values, but remember in the equations you want to do radians, right? Okay.
So the circumference is 2 pi, then the pi be 180.
Yeah. So pi radians, that is true. Pi radians is equal to 180 degrees. Right. Sometimes that's a handy conversion too, right? To have that pi radians, 180 degrees, same thing. 2 pi radians, 360 degrees. Yeah, no problem. All right, so got that. Oh, because what number goes right there? It's 0.14 radians per second. Okay, that's how fast the thing's spinning. Right. Or I guess if you did 360 degrees, you could have done 8 degrees per second. Would also get you there. Same answer. I'm gonna do 0.14 radians per second. Okay. And we're solving for time. So there's one algebra step. You guys, what's the one algebra step? Divide both sides by 0.14 radians per second. Time is 2 pi radians over 0.14 radians per second. I'm getting 44.9 seconds. All right. About 45 seconds. Okay. All right. So big picture, let's go back and see the forest for the trees here. If you see O'Neill cylinder out in space with a 1 kilometer diameter, that's to say a 500 meter radius, and it's spinning so that all the people on the inside surface think that they're standing on Earth, then the only way for that to happen is it has to be rotating 0.14 radians per second, which is about 8 degrees per second. Okay. And therefore, it makes one complete revolution every about 45 seconds. Okay. All those align, they all come together. All right, okay. All right, are we good? All right, let's move on to the next thing, which is this page. You guys got this page? All right, so this is just extra notes for you guys, but we're going to do this in class right now. Then you guys get some extra notes. And so this involves this turntable. Look at that. This is a picture of this turntable right here. Right? Like this corner right here. This corner right here. Couldn't it? Right? Some radial distance. The whole thing. This thing turns. All right. So what first thing it says to do is to do 3 revolutions at constant angular velocity. So we're just going to do step by step. Right? Going to do some equations. Going to do some graphs. Okay. See what this looks like. We're going to start here, so that this is zeroed out. Here's my x-axis where it all zeroes out. Okay, let's do 3 revolutions at constant angular velocity. Ready? And go. 1, 2, 3. and then I take my hand off and it slows to a stop. Okay, that'll good? Okay. So, oh, I gave you guys a number. I shouldn't have done this, but see where it says what angular displacement was it? I put 6 pi. Could you guys figure that out though? I mean, if 2 pi radians is 1 revolution, then 6 pi radians is 3 revolutions. Okay, so you guys do that. Great. And how much time did that take? I think I just gotta make something up. Suppose it was like 5 seconds. 5 seconds to do that. Okay, do it 5.0. Okay. Hey, if you know how far it turned and how much time it took, can you calculate how fast it was rotating? How would you solve that number? Would you do that divided by that? Right? How far it rotated divided by how much time? You get this radians per this seconds. Right? I'm going to take 6 pi radians. That's how far it turned. And divide by the 5 seconds. And it took 3.77 radians per second. That's how fast it was rotating, right? Right? Is that okay? Okay. Next set says release and allow to slow to stop. Now I did that, and I'm going to fudge this a little bit, but sort of something really similar to what I did. Okay. But please zoom out so you guys can see this better. Okay. So I went around 3 times, zoom, and then I let it go, and it was a slow to stop. Okay, I'm going to fudge this a little bit, but it was approximately there. Okay. Which was, if you look at this angle, I'm going to zero this out. It swept out about 135 degrees, about 135 degrees. Okay. Okay. And that was pretty close to what it did. Now, 135 degrees that it turned, right? Remember, we're not measuring in degrees, we're measuring in radians. How many radians is that? Let me show you guys 2 different ways to approach that. Okay. Now, I'm picking 135 degrees, one, because that's pretty close to what it actually did. But for another reason, because that's a very nice looking fraction. Okay. We're trying to figure out what is this angle right here. Okay. So I went around 3 times, and then let it go at this point, and it was slow to stop right about there. Right. Now, how many radians is that equal to? Does anybody know before I start telling you guys the answer? How many radians? Yeah.
I think it's 25 and 57.
It's here. How about this? This is like 0 degrees, 0 radians is this axis, right? Right. And if you go all the way around, that's 360 degrees or 2 pi radians. Is that true? Right. How many radians right at this moment? Yeah, 1 pi. They just call it pi, right? Right. Oh, wouldn't this be like pi over 2? Oh, if you guys have been through a pre-calc class or a trig class, you're probably familiar with the unit circle. I'm sort of doing that, right? Okay. And hey, is this like 3/4 the way over to pi? Is this like 3/4 of pi right here? Is that what that is? Okay. That's actually the answer. 3/4 pi. Okay. 3/4 of pi radians. What is 3/4 of pi? That is 2.36. This would be radians, so it would be radians. 2.36 rads. Okay. Here's, I told you guys I was going to show you 2 ways to get to that number. So let me show you guys a different way to get to that number. I measured this with a protractor because that's our measuring tool, and I got 135 degrees. So zero this out, scoops through. Yeah, about 135 degrees right there. Okay. So if I do 135 degrees, remember, I don't want degrees in my calculations, but that's what I measured with. I can convert this into radians. Guys, how many degrees in degrees to radians? What's the conversion?
57.
What's it?
57.
Oh, yeah, that's one way you could do it. I could do 57 degrees per 1 radian. So what's 135 divided by 57? Bam, it's 2.36, which is the same thing. Bam, that's one way to do it right there. Right. If you want more digits of precision, you can play off either the pi or the 2 pi. Let me play off this pi. Right. So there could be pi radians per 180 degrees. 135 times pi on 180. Right. 180 over pi, by the way, is about 57 degrees per radian. Okay. And it's the same thing. So there you go. So there's 3 different ways. So they're all leading to the same number of radians, though, right? Right? No matter how you do it. Okay, so when it slowed to a stop, it took 2.36 radians to do that. Okay. All right, everybody good? All right, and the time to come to a stop. Okay, here's what I'm gonna do. Something that's probably pretty close to reasonable. I'm gonna say 1.25 seconds. There's a little bit of a math story behind that number. We're gonna run with it. We're gonna say, hey, that was pretty reasonable. So I took my hand off, it slowed down to a stop. Let's took about a little over a second. Second. Okay. All right. Oh, and if it did come to a stop, here, I filled in the next cell for you. But omega final is 0 radians per second, because that's go to a stop. Okay. All right. Let's skip the next cell and go to the very last cell where it says alpha. Now, alpha is the rate that it's slowing down rotating, right? Because it was slowing down rotating. At what rate? Oh, we're about to solve that right here. Okay. So, do you guys think that that could be these 3 kinematic formulas, right? You can just pick your favorite one and run with it, right? So, let's say I like this metal formula, just for example, right? Because I know it went to 0 radians per second. It was going from this 3.77 radians per second, right? And it took 1.25 seconds to do that. So could you solve for alpha, like the rate that was slowing down? Okay. How about we could do that? So I'm gonna go omega final equals omega initial plus alpha times t, right? I know this went to 0 radians per second from 3.77 radians per second. And it took it 1.25 seconds to slow to a stop. Right? Okay. So see, can I subtract this over and divide by that number? So 1.25 seconds times alpha is equal to negative 3.77 radians per second. Divide both sides by 1.25 seconds. -7.5. Negative 3.0 radians per second squared. Radians per second squared. That could describe an angular acceleration, which of course it does. See how the variables in the units all match up, right? Right. That's the rate that it's slowing down. It was losing 3 radians per second every passing second while it was slowing down. Okay. Right, so back to this page. Under alpha, oh, I even gave you guys the negative sign to remind you guys it was slowing down. 3.0 radians per second. All right, is that okay? All right, you guys good? Okay, who's got 8 questions so far? Okay. All right, so next deal, let's skip over here and do these graphs. You know, there's 2 sets of graphs. There's angular motion graphs and back to the classic linear motion graphs. So the angular graphs, this one says theta versus t, so it's theta in radians versus time in seconds. The next one says omega versus t, so that's your angular velocity, radians per second, versus time in seconds. And the last graph says alpha versus t, so that's angular acceleration, radians per second squared, versus time in seconds. Okay. Okay, so you guys get those 3 graphs? Okay. You know what? If you guys can stay a step ahead of me, then that'd be a really good indication that you guys know how to do this stuff, right? Especially if you're using a pencil. If you get some wrong, you just erase it. Okay? I'm gonna do what I've usually been doing all year, which is start with the middle graph and then branch out from there. So just keep consistent with that. Okay. So remember, this is a 2-part story. The first part of the story is I was just rotating at a constant rate for 3 revolutions. And then I took my hand off and it naturally slowed to a stop, right? So we have the constant velocity part, and then we have the slow to stop part. Okay. And the time where it switches, I put a little tick mark on the time axis. You guys see that tick mark, right? Okay, so that's where it's gonna stop doing one thing and switches over and start slowing down. Okay. So can you guys draw what the middle graph would look like for constant angular velocity? When it's just going around for the first 3 revolutions. Right? It took 5 seconds to do that. Right? It's just right? It's just going around constant. Okay. Did you guys just draw? I hope you guys have it by now. Did you guys just draw this? Just like that. Okay. Because the angular velocity was constant. Okay. In fact, I can tag a number to that. I can say it's this number right here. 3.77. Isn't that true? Right? And that's going to be radians per second, but that unit is already embedded in the axis. Is that true? Okay. Then I took my hand off and it slowed to a stop. Can you guys draw the rest of the graph where it's slowing to a stop? Slows to a stop. Is you slows to a stop? Now, slows to stop, doesn't that mean final angular velocity is going to be 0 radians per second? Okay. If it slows down uniformly, I bet it looks a lot like that. You guys draw something like that? Okay. Or this is 5 seconds, and this would be what, 6.25 seconds? Okay. Little trapezoid looking shape right there. That's all right. Okay. Right, let's go hit the top graph. Theta versus time. Right, so angular displacement versus time. Yeah, I'll give you guys 1 point to start out. At time 0, it hadn't moved anywhere yet, but then it started going. Okay. In fact, during the first about 5 seconds, it was going at a constant rate. Right, it was picking up displacement at a constant rate. I had it going counterclockwise. Let's call it the positive direction. Did you guys just draw this? Right? Where it was picking up angular displacement at a constant rate. In fact, what is the slope of that line equal to? Is it picking up 3.77 radians every passing second, which is this number right here? Right? Is that true? 3.77 radians per second, 3.77 radians per second. Right? And then right at this moment, I took my hand off and it slowed to a stop. Hey guys, when it slowed to a stop, was it still moving in the positive direction? Yeah, it was still picking up angular displacement. It was just doing it slower and slower and slower. It was slowing to a stop. Right? So it was still moving forward. Do you guys remember what the graph looks like, displacement versus time, for a car braking to a stop? Because I bet this is going to look very similar to that. Right? Yeah, go ahead.
Parabola? Yeah,
Yeah, exactly. It's an upside down parabola with the vertex right there. Bam. It's that little hook. Okay. So it's a straight line that leads into an upside down parabola. That little hook right there with the vertex right at the top. All right. And that's exactly where it stops. Okay, guys good there? Okay. All right. And finally, angular acceleration as a function of time. So what do you guys think the story is while it's doing constant angular velocity? What's the acceleration equal to?
Yeah.
Yeah, 0, right? Because it's not speeding up or slowing down, rotating, right? It's just 0 angular velocity because, or sorry, 0 angular acceleration because constant angular velocity. Okay. And then when I took my hand off, it slowed down. It slowed down to a stop. Ah, we got a number for that, didn't we? We said -3 radians per second squared, right? Isn't that like, so it's on this graph, -3.0. So didn't it do this? Just like that. Okay. So in physics, if you like jumps, you can draw jumps. If you don't like jumps, then you can connect it like this. Okay. So some version of that, right? But basically, there are 2 different angular accelerations. There's 0 angular acceleration during the constant angular velocity part, and then there's a negative constant angular acceleration while it's slowing to a stop. Okay. You guys good? Okay. Now, everything we've done on this page so far, these table values, these graphs, all refer to angular motion. Actually, just one, let's go, I can hit this last one, then we'll go hit all the linear stuff. Okay. So average, guys, what's the average of 3.77 and 0? 3.77 over 2. I'm looking at 1.88. Okay, this number would be like 1.88, about halfway between. Okay, I'm gonna throw that in right here, 1.88 radians per second. Okay, that could be useful maybe if you do average velocity times time would be the same thing as finding the area under the curve velocity versus time. Might be a little faster way to do it. Okay. Anyway, I don't want to dwell on that because we've got a few minutes left and I want to hit all the linear stuff. So we need to figure out, we need to connect this back to the like August physics. So let's focus on, I have to pick one of these points. I'm going to pick the one on the very outside. Okay? And that guy is 14 centimeters from the center. I see 14 centimeters. Got 0, 7, and 14. Right. So see where it says R? I'm going to put 14 centimeters. Okay. And then I wrote a bunch of equations here, but those equations are basically just all the stuff going on. Okay. Got that, got that, got that. Okay. Yes. So all your notes. So what distance did that Roosevelt go during the first 3 revolutions? Well, can I just take, okay, isn't X just equal to theta times R? Is that true? 3 revolutions, that's 6 pi radians at 14 centimeters. Just multiply that together, get how far, like distance, 6 pi times 14. All right, I'm looking at 264 centimeters. Okay, is that okay? Okay. Woo, that's a long distance. That's like 2.5 meter sticks, isn't it? Okay, I can believe that. I mean, it's 3 trips around the circle, 14 centimeter radius. Yeah, that's about right. Right. Oh, hey, different question. What is the displacement? If you start and end at the exact same spot, what's your displacement? 0. But this question is not displacement, it's distance. So distance 200 something centimeters, displacement would be 0. Okay. All right, a little excited there. How about speed? Notice I'm not saying velocity because that would also be 0, but speed, right? What, like radar gun speed? If I point a radar gun at this guy, well, I know this guy's velocity, angular velocity was this many radians per second, and the linear speed would just be the angular velocity multiplied by your radial distance from the center. Okay, so I got 3.77 radians per second at 14 centimeters from the center. 3.77 times 14. I'm looking at 53 centimeters per second, rounding a little bit, 53 centimeters per second. You guys get that? Okay. Here's the thing. I know we're about to run to the bell here, so here's what we do. You guys could probably figure out the rest of these yourselves, I think, based on the notes I just gave you. Here's what the graphs look like. The graphs have the exact same shape as the 3 graphs that we just did. Right. Now the axes are different, the numbers are different, the units are different. Well, except for the time axis, that's the same. Right? But in terms of the graph shapes, like you could like stretch and warp them and lay them right on top of each other, and they would look identical to the 3 graphs we just did. But this is X versus T, V versus T, and A versus T. Right? All right. So where are you guys gonna be tomorrow? Cafeteria. Oh, unless you think you're taking the PSAT, I uploaded on Google Classroom a list of all the students where they're going to be. Think you're taking it. If you think you're taking the PSAT, then pick Google Classroom. If you're not taking it, then go to the cafeteria tomorrow, draw an O'Neill cylinder panel, have fun, and I will see you guys the day after. Yeah, you too. Have a great day.